Welcome back, everybody. Today we're going to be switching gears toward the end of our unit here. We're looking at quadratic functions versus quadratic equations. So we spent a lot of time solving quadratic equations. That's where your equation just has one variable to solve for, right? Just solving for x. If you're looking at a quadratic function, so it's still quadratic. That means you're looking for an x squared, but instead of just the x being the only variable in the equation, now we're going to be looking at x and y in the equation, and then we have a relationship between a function that we're trying to graph. Okay, so quadratic function, a function, let's start there, is an equation that's relating two variables, and those two variables are usually x and y. And remember, there's a little more to the definition of a function. It has to be passing the vertical line test. It has to be true that every x value corresponds with exactly one y value. So if we have that, and your function is quadratic, then in that function you're going to see a degree of 2 on x. So you're looking for an x squared. So we're going to be looking at the graphs of quadratic functions today, and we're going to start with the parent quadratic function. And the parent quadratic function is it's like the basis for all quadratic functions. It is the one quadratic function that all other quadratic functions are based on. And the parent is exactly what makes it a function, the y and the x in your equation, and what makes it quadratic is the square on the x. So the parent quadratic function is just y equals x squared. Nothing being added to it, subtracted from it, multiplied by it, dividing into it, nothing. So there it is, there is the basic. So all quadratic functions that take this and manipulate in some way, they are all just going to be some transformation of this parent function. Okay, so we looked very briefly at graphing in chapter 7. We said if we wanted to make a graph, we could just make a table of values, right? Where we pick maybe some negative numbers, 0, some positive numbers like -2 to +2. We plug them in, and then we plot the points. So if I plug in -2 for x, -2 squared makes our y value 4. Plug in -1, -1 squared makes a +1 for our y value. Plug in 0, 0 squared is 0, +1 squared is 1, and +2 squared is going to make 4. So I apologize, the graph might not be too clear for you if you printed this out, but over here is -2, and we have a y value of 4, and -1, 1, 0, 0, we have a point, 1, we have a point, and then 2, 4, we have a point. So hopefully this is looking familiar, because I think we graphed a quadratic before. But we're seeing a U-shape form here, so we could keep picking x's, which means this graph will continue. Picking larger x's, we can continue picking smaller x's, so this graph will continue this way as well. So all quadratic functions make this U-shaped graph, and we call it a parabola, not a parabola. Okay, so it's a parabola, and we say that this parabola in particular is a parabola that opens up. And it's possible for the parabola to also open down, but from this point here, which we call the vertex of the parabola, we'll talk more about that in a second, from that vertex the graph goes up. So we say this parabola opens up, okay? So the vertex, along with a few other features, other characteristics, or things we have to be able to identify from our graphs, from our parabolas, from any function, but let's talk about parabolas in particular. So the vertex is what we call the turning point of the graph. It's where your graph turns from increasing to decreasing. So if we were to read this graph from left to right, if I started on the left end of the graph and I just followed it, I'm going up, going up, going up, going up, going up until I get here, which is where the vertex is at, and then it turns, and after the vertex, the graph is going down as we follow it from left to right. So we call it the turning point because it changes directions at the vertex. So this point right here is the vertex. It is the turning point of the graph, and in this case, it is the maximum point on the graph. It is the highest point on that graph, and that will happen if your parabola opens down like this one does. Right, this parabola opens down, and if our parabola opens up like the parent function did, then we could see that the vertex is the minimum. So this vertex is a max, and this vertex is a min. So your vertex will be the maximum or minimum point, the highest point on the graph if it opens down, or the lowest point on the graph if it opens up. And let's see what else. We should also be able to identify the x-intercepts. And x-intercepts have a couple of other names. We can call x-intercepts roots, or we can also call them zeros. And these are the points where your parabola touches the x-axis, and that should make sense, right? An x-intercept, where does the graph intercept the x-axis? So in this particular case, our parabola touches the x-axis. The x-axis is this one, okay? Where does our graph touch that axis? Right here. So we have a root, an x-intercept right there, and then it also touches here, so we have a root or an x-intercept there. So it's possible for your graph to have two x-intercepts. Not the only possibility. I mean, if we were to shift this graph down a little bit, let's say the vertex of our graph was on the x-axis. In that case, we would only have one root. Or let's say we made a graph where the vertex was here and it opened up, then it's possible for this thing to never touch the x-axis. So there could be 0 x-intercepts, there could be 1 x-intercept, or there could be 2. Most of the time, it's going to be 2, but 0, 1, or 2 are all options, okay? Then we have the y-intercept. The y-intercept is going to be the point where your parabola touches the y-axis, and there will always be exactly one y-intercept. So no matter where your graph is, eventually it's going to hit the y-axis one time. So there's our one y-intercept, right? No matter where your parabola is, eventually it's going to touch one time on the y-axis. Okay, so one y-intercept. And the last piece here is called something called the axis of symmetry. I'm sure you've heard the word symmetry before. Symmetry has to do with sameness, and we have symmetry in every parabola that we draw. And the symmetry happens around the vertex. If we were to fold the parabola in half over the vertex, if we were to make a vertical line here through the vertex and fold the parabola in half over that line, the two halves would match up exactly. They are symmetric, exactly the same on either side. And so that vertical line that goes through the vertex that cuts that parabola exactly in half is called the axis of symmetry. So it's a vertical line. It goes through the vertex. Vertical line that goes through the vertex, that cuts the parabola in half. And your axis of symmetry is always going to be stated using an equation. So if I said, where is the axis of symmetry? That is a vertical line. Vertical lines are x equals equations. And this vertical line happens to be going through an x value of 3. So we would say our axis of symmetry is at this vertical line, x equals 3. And let's put that in here. This is always an x equals equation. Your roots, just to reinforce here, these are always on the x-axis, which means the y value would be 0. So this root is at 4, 0. This root is at 2, 0. So at your roots, the y is always equal to 0. And then at your y-intercept, this one happens to be at 0, 8. If it's on the y-axis, the x value has to be 0. Okay? So those are some characteristics from our parabolas, our quadratic functions that we should be able to identify. Now, if I give you a graph like the one I have here, it shouldn't be too big of a deal to establish where those things are, but eventually we'll be able to find those characteristics without graphing as well. Now, if we wanted to graph any quadratic function, like this one shifts around, right? You can still see it's a parabola, but it's not in exactly the same place the parent function was. We have to be careful about how we make our table. I'll go to my scratch paper for a second. So let's say I wanted to graph a function, another quadratic function. Let's say x squared plus, 8x plus 15, okay? Let's say I wanted to graph that so that I could identify where the vertex was, where the intercepts were, where the y-intercepts were. I just wanted to see what this parabola looked like. If I try to use my same approach, where I make my table, and I pick -2, -1, 0, 1, and 2, which, those are standard numbers, they generally will work, what's going to happen here? So if I plug in -2, I would have y equal to -2 squared plus 8 times negative 2 plus 15. So that's 4 minus 16 plus 15. It's negative 12 plus 15, which is 3. So I get a y value of 3. Okay, let's do that again. Let's see what happens when we plug in a negative 1. Negative 1, negative 1. So I get 1 here, and then minus 8, and then plus 15. That's negative 7 plus 15, which is 8. All right, let's plug in 0, and trust me, this is going somewhere. Plug in 0, then I get 0 here, and 15 left over. Okay, let's plug in 1. 1 here and 1 here, so this is 1 plus 8 plus 15, and 9 plus 15 is going to make 24. And then lastly, let's plug in 2. So 2 here and 2 here. So this is 4 plus 16 is 20, and 20 plus 15 makes 35. All right, so now you might be able to see this table looks a little different from the one we had in our parent function, right? Let's go back to that one for a second and look at this table, and maybe you're seeing the same symmetry that we see on the graph we see happening in our table, where negative 2 and positive 2 created the same value, negative 1 and positive 1 created the same value, and then we had that vertex right in the middle, right? Well, let's see what's happening here. Do we see the same thing? Same thing happening here and here, or here and here, or here and here? No. So when we go to graph this, let's see, we're going to go really ridiculous on the y's. Okay, so 1, 2, 1, 2, and then let's just say 10, 20, 30, 40, okay? Just to make this sketch real quick so you can kind of see. So at negative 2, we ended up at 3, so like somewhere here-ish. And then at negative 1, we were at 8, so we're higher. And then 0, we're at 15. And then 1, we're at 24. And then 2, we're at 35. So I see a little bit of a curve here, but what's the issue? Well, this isn't the whole parabola, right? In order to make a graph and visualize the parabola that we're trying to examine, we have to capture the whole parabola. So not just one piece of it, but I need the whole thing, right? I need the vertex specifically, and then what's happening on either side of the vertex. So this table of values approach is still a good approach, but it's only going to be helpful if the vertex is right in the center. So we need the vertex to be in the center, and 0, 15 is clearly not the vertex of this parabola. It's not changing directions at that point. So we want to make sure we have the vertex in the center, and then we build to the left and to the right of that vertex. So there's a couple of ways we can ensure the vertex goes in the center, and it depends on the form of the quadratic function that we're given. So that's where we're going to head next, okay? So we're going to look at what we call vertex form first. The vertex form of a quadratic function is really nice because it shows us where the vertex is. So in vertex form, you're going to see a function that looks like this. You're going to have y equal to a times x minus h squared plus k. Now, can you still see the parent function in there? Right, our parent function is the y equals x squared. There's the parent function. All we're saying now is what is going to happen to the function if we add and subtract and possibly multiply it by something. Well, it's going to move the function around. It's going to affect it. You're still going to have a parabola because this is still a quadratic function, but what's going to happen in this form in particular is h and k are going to shift our graph. They're going to affect where the vertex of the graph goes. So we're going to call this vertex form because it shows us the vertex. The vertex is going to be at h and k. So this number here and this number here. Well, in fact, the opposite of this number here. So notice we have a negative h in the formula here, and then a positive h here. So notice the sign changes for h, but it's the same for k. Positive k here, positive k here. So if we have a quadratic function in this form, we can literally pick out the numbers to figure out where our vertex is. So we need to make that vertex the center of the table, and then we're just going to choose values to the left and right of that vertex to create the entire U shape on our graph, okay? So this is vertex form. Whenever you see the parentheses in the square, That's your clue that this is vertex form. So I can tell where the vertex is by changing the sign of this number and then keeping the sign of this number. So that vertex is going to be at -3, -4. So change the sign of the one that's in the parentheses, and that arrow is a little off. Keep the sign of the one that's after the parentheses. So this one changes, and this one we keep. Okay, so I know my vertex is at -3, -4, so I'm going to make my table of values, and I'm going to put -3, -4 right in the center. So I know my vertex, I'm going to go ahead and plot this point, is at -3 and -4. So it's right there. Now I just need to know what's happening to the left and to the right of that vertex. So I know what's happening when x is -3, but what's happening here and here and here and here? Let's make this parabola go out a little farther, right? So I'm going to go to -2 and -1 and -4 and -5. I'm going to go to the left and to the right of that x value and see what's happening, okay? So I'm going to plug in -1. If I plug in -1, I'm at -1 plus 3 squared minus 4. So that's going to be 2 squared minus 4, or 4 minus 4, which is 0. So I'm going to get a 0 here. And because there's going to be symmetry around the vertex, there's going to have to be a 0 here when I plug in the -5. Now I'm going to show you just to verify. If I plug in a -5, what happens? Well, when I put -5 in here, -5 and 3 makes a -2. -2 squared is the same thing as +2 squared, so I still end up with 4 minus 4, or 0. So if the vertex is in the center, then these two y values should be symmetric. They should be the same, so you shouldn't have to plug both of them in. And then that will be similar for these two y values, here and here. So when I plug in -2 here, what happens? When I plug in -2, -2 and 3 makes 1. 1 squared is 1, and 1 minus 4 makes -3. So I get a -3 here. Now I'm going to show you, but I know there's going to be symmetry, so I should get -3 again here. So if I plug in -4, I'm going to plug -4 in. -4 plus 3 is -1. -1 squared is +1, and 1 minus 4 is -3 again. Alright, so when we go to make the table, I don't actually have to fill in the whole table. If there's going to be symmetry, I just really need the first half, and the other half will kind of follow. Okay? So now we have 5 points. We can make our parabola. So we have a point at -1, 0. That's here. At -2, -3. At -3, -4 is our vertex. We plotted that. -4, -3. And then -5, 0. And there we have our graph. Now if I wanted to go one more out in my table, just because I can see it's going to end up crossing the y-axis on the next point, let's say I put one more point in here, -6. If I plug in -6, -6 plus 3 squared minus 4, -6 and 3 would be -3. If I square that, I get 9, and 9 minus 4 is 5. So if I get 5 here, at -6, I can go up to 5, and because this graph is symmetric, at 0, I can go up to 5 as well. So now I have a really nice set of points to connect and make this picture. And just to reinforce, right, here's our vertex. And this vertex is at the bottom of the graph, so we would call it a minimum. We have a root here. At -1, 0. We have a root here at -5, 0. And remember, root is just another word for an x-intercept. And we have a y-intercept here at 0, 5. And it's not like you're not going to have to identify all of those pieces every time. I'm just trying to reinforce what we're doing. And just so you can see it too, here's our axis of symmetry. So we have an axis of symmetry, and that's going to be at x equals that x value that that line is going through is the same x value in the vertex, that's -3. Okay, All right, so next one, we're going to try this again. I'm not going to go through labeling all the parts, but just let's try to make a graph for this parabola. So this is in vertex form. The vertex, when I have the parentheses and the square there, that's when I know I'm looking at vertex form. So I want to, for my vertex, change the sign of the number that's in the parentheses, so -1 here, and then we're supposed to keep the sign of the number that's out here. But notice there's nothing being added or subtracted after the parentheses. That means we're not going to be moving in that direction, so there's just going to be a 0 there. Okay, so we have change that sign and then keep that sign, but there's nothing out there, so that's why we've got a 0. So I'm going to make my table, and I'm going to put my vertex of -1, 0 right in the middle, and then I'm going to go to the left and to the right. So I'm going to go, let's say 0 and +1 and -2 and -3. So I want 5 consecutive numbers in there. Okay, so let's plug in, doesn't matter where you start, I'm going to plug in the 1 first. I plug in 1 plus 1 squared. 1 plus 1 is 2. And then remember exponents before multiplication, so 2 squared makes 4, and 4 times -2 makes -8. So if I get a -8 here, then I'm going to get a -8 here as well. If that's really my vertex in the middle, there's going to be symmetry around that vertex. Okay, so now I'm going to plug in 0. Put a 0 here, and see what happens. If I put a 0 here, 0 plus 1 is 1, 1 squared is 1, and 1 times -2 is going to be a -2. So if I get a -2 here, I'm going to get a -2 here as well. And now we should have enough points to make ourselves a nice parabola. So let's graph. At 1 and -8 we have a point. At 1 and -8. And then at 0 and -2. And then at -1, 0. And then at -2, -2. And then at -3 and -8. So there it is. And notice, I want you to notice a couple of things. So if we look at this function here, looks just like the parent function. It still opens up. Even the width looks the same. It's just shifted. The whole thing shifted to the left and down, and that was because of the vertex there. But if you notice, this parabola opens down. And why do you think that this one opens down versus where the other two opened up? And this one is going to open down because of the negative here. So this one opens down because of this negative. This negative is why this graph opens down. When there's a positive number out in front, it's going to open up just like the parent function did. Stick a negative out there, it makes it open down. And that 2 that's out there is why this parabola looks a little narrower than the others as well. So this parabola opens down, and then this parabola opens up. Okay, so there it is. If it's in vertex form, we can pretty easily identify the vertex, make that the center of the table, and then build around it to make your picture. Now if we have standard form, it's not as helpful. Standard form is one that should look familiar. It's where we have the ax squared plus bx plus c. It's the same standard form we look at for equations, but now there's going to be a y equals because it's a function. So if this is the form, notice there's no h and k. So let me go back here for a second. H and k tell me where my vertex is. There's no h and k here, and I can't tell where my vertex is just by looking, okay? So we can actually use a formula to calculate the vertex. The first coordinate of the vertex, which we call the h, there's a formula for. H is just going to equal -b divided by 2a. -b divided by 2a. And then the other half of the vertex, the k part of it, we can find like we find any other point. If I plug in an x value and I want to find the y value that goes with it, you just plug right into your function. So you're going to plug, by plugging h into your original function, you can calculate the value for k. So then you make your table with that vertex in the center, and the rest of the process is the same. So can't tell by looking at this standard form where the vertex is. I do know that it's going to open down because of that negative in front, but I don't know where it's going to open down from. So to find the vertex, I'm going to use a formula. All right, so my vertex has two pieces, h and k. The first part of that, right, we're going to have a vertex at h and k. The first part of that, I use the formula to calculate. So h is going to equal a negative b, remember use parentheses when you plug in, and then 2 times a. So remember, just like the quadratic formula, here's a with -1, here's b, -6. So a -6 over 2 times a is 2 times -1. If we simplify, that's +6 over -2, which is -3. So now I know the first half of my vertex is -3, right? Think about if you're making a table, right? If you knew that the first half of the point was -3, how do you get the other half? We'll plug the -3 in. So if we take that -3 and we plug it in, k is going to equal negative, instead of, if I plug it in, so I'm taking this and I'm plugging it into this function, okay? I'm going to plug in -3 squared minus 6 times -3 and then minus 9. So k is going to equal, that's a -9, feel free to use your calculator, just so you don't make little mistakes like I tend to do. -3 squared, and then minus 6 parentheses -3, and then minus 9, and we end up with 0. Okay, so this means these two things tell me here that, let me get rid of this so it's not confusing later, that these two pieces tell me that my vertex is at, let's fix this, -3 and this 0 here tell me my vertex is at -3, 0. Okay, so now I'm going to make my table. Whoops. I'm going to make my table. And I'm going to put -3, 0 right in the center. And then I'm going to go to the left and to the right of -3. So make those 5 consecutive numbers. And then I'm just going to plug a couple of them in. Because there's symmetry, remember I don't have to plug everything in. So let me plug in the -1. We have y equal to a -1 squared minus 6 times -1 minus 9. So this is going to be -1 plus 6 minus 9. That's 5 minus 9, which is a -4. So a -4 here, and a -4 is going to happen again here. Now I'm going to plug in, whoops, goofed, the whole darn thing. I'm going to plug in -2. So a -2 squared minus 6 times -2 minus 9. So that's 4 times a negative makes that a -4 plus 12 minus 9. That's 8 minus 9, which is -1. So a -1 here, and then again a -1 here. Alright, so now I should have enough points. I'll plot this graph. I'm going to make a point at -1, -4. Another one at -2, -1. -3, 0, at -4, -1, and then -5, -4. And so we can connect and make our parabola. Okay? So we have another parabola that opens down. I knew that was going to happen. And see, this time we only have one x-intercept because the vertex is on the x-axis. All right? Let's try that again. So this is another, and feel free to pause if you want to try it. But this is another one in standard form. I cannot tell where the vertex is by looking at it, so I'm going to have to calculate it. So a is 1 and b is -6. So we're going to calculate h. H is -b over 2a, that was the formula. So -6 over 2 times 1. This time is +6 over 2, which is +3. And then to find the other half of the vertex, I'm going to take that 3 and I'm going to plug it in. So I'm looking at 3 squared minus 6 times 3 plus 4. So that's 9 minus 18 plus 4. That's -9 plus 4, which is 5. So k is going to equal 5. So these two pieces here, the 5 and the 3, right, those are telling me my vertex is at 3, 5, h and then k. So now I can make my table, and I could put that vertex 3, 5 right in the center, and then just go left and right, make 5 consecutive numbers here so we can make a good picture. So now I'm going to plug in the 1. So I would have 1 squared minus 6 times 1 and then plus 4. So that's 1 minus 6 plus 4, or negative 5 plus 4, which is a negative 1. So negative 1 here, negative 1 here. And now I'm going to plug in 2, although you could have chosen to go with the 4, it doesn't really matter. I'm going to plug in 2 here. So that's 4, that's negative 12. 4 minus 12 is negative 8, and negative 8 plus 4 is negative 4. So a negative 4 here, and a negative 4 here. All right, now we have enough points that we can put this all on the graph. So I'm going to plot a point at 1, negative 1, at 2 and negative 4, at 3 and 5. What did I do here? Oh, this is a goodness. You see what happened, and hopefully you catch yourself doing this too. If I go to 3 and then positive 5, that's not lining up with what I was doing, so I knew I made a mistake, and you guys are probably screaming at me from the other side of the screen, but negative 9 plus 4 is a negative 5, so that should have been a negative 5 there. If I go to 3, I need to go down to negative 5, the vertex, and then I'm going to bounce back up to negative 4, and then bounce back up to negative 1. Now, if I wanted to be more accurate here, I could plug in the 0 and see one more level where this goes out, because then it's going to hit both the axes, and I would probably do that. If I plug a 0 in, 0 squared minus 6 times 0 plus 4, right? That's all gone, so it's going to be 4. So if I plug a 0 in and I get 4 on this side, it means over here I can go up to 4 and have that symmetric point. Now I have a really nice parabola. Again, a parabola that opens up because the number in front, a, was positive. And I forgot to point that out too. So in our vertex form, a x minus h squared plus k, they share this. That's the same a in both functions, okay? And they both have the y equals x squared, right? The y equals x squared. They both have the parent function. It's just when you change a to something other than 1 and you add and subtract and multiply the things, it manipulates the parabola, right? But because they all have that parent function in there, they all make parabolas, okay? All right, so we should be able to make a table of values and graph. Now, if you have been using Desmos, Desmos graphs for you too. So if you, let's say you wanted to put this in Desmos, or let's say you have a graphing calculator, right? If you just typed in the function y equals, I'm looking at number 4 here, x squared minus 6x and then plus 4, it makes the same picture that we made on the paper, and it was a lot less work, right? So if you want to verify what you're doing, or you have a graphing utility, by all means you can use it, but some of these things you should be able to do by hand. Now if you just tap on the graph here, it actually shows you values too. So we can see, if I tapped on that point, it shows me that that's my vertex. If I tap on that point, well, the x-intercepts aren't exact, but I can tap on this point here at 0, 4 to confirm my y-intercept, and the x-intercepts are a little ugly, but that's because they weren't exact values here. So if you have a graphing utility and you want to verify what you're doing, by all means, you can do that, okay? Now, some of the features that we talked about along the way are features that you should be able to calculate without, making the graph first, and sometimes you just can't see exactly where these things are anyway. So what characteristics should we be able to find without graphing? One set of those is the max or min value. And the max or min value has to happen at the vertex. So it has to happen at the vertex, but technically, what is the max or the min value? So when you have a graph, and let's say that this is your vertex here, and let's just say that it's at 3 and 2. Which one of those is actually considered the maximum value? Well, the x value here is telling me how far to the left or right I'm going, but the maximum, we call this a max of being at the top, that top maximum value is really referring to the y value that it corresponds with. So the max or min value is always going to be the y value that is at the vertex. So if I give you a function and you can tell me where the vertex is, then that y value in that vertex will always be the max or min value of that parabola. Okay, so here This is technically vertex form. Can you see how if I put x minus 0 squared minus 4, that is the same function? So we're not adding or subtracting anything to the x. We're just subtracting 4 here. So my vertex would be at 0, 4. Okay, so here, let me get rid of this. My vertex is at 0 and negative 4. And the y value here, y equals negative 4, is the, just need to determine if it's a max or a min. So how do you know? Well, is this vertex at the top of this graph or is it at the bottom? Well, right in the front of this function, a is a positive 1. That means this parabola opens up. So if the parabola opens down, that means the vertex is at the bottom. It is a minimum. So y equals 4 is the minimum value. Okay? Now, the second one here is not going to be as clear because I can't just tell where the vertex is by looking at it. This is one where I'd have to calculate the vertex using my formula. So h is going to equal negative b over 2 times a. That's 4 over 4, which is 1. If I plug that in, then k is going to equal 2 times 1 squared minus 4 times 1 plus 1. Just use my calculator. So 2 times 1 squared minus 4 times 1 and then plus 1 is a negative 1. So now I have a vertex at 1 and negative 1. So this is my y value. So y equals negative 1 is the max or min. It's the same as the other one, right? This positive here, this positive 2 here. Where can I fit this in? Because a is a positive 2. Again, we have a parabola that opens up, and so the vertex is at the bottom, which makes it a minimum. I suppose I should have made one of those negative. That's my bad. Okay, so if we can identify the vertex, the y value in the vertex will always be the max or the min, depending on if it opens up or down. Okay? All right, the next piece we have to be able to identify is our axis of symmetry. And the axis of symmetry, we know, again, has to go through the vertex. And we said it's always an x equals number, an x equals equation, and so it has to match the x value at the vertex. So again, if we can identify the vertex, then the x value at that vertex will be where our axis of symmetry is. So here's one in vertex form. I can see my vertex is going to be at positive 3, positive 1. Change that sign, keep that sign. That is the x value. So x equals 3 is our axis of symmetry. So we have an axis of symmetry. Say this, axis of symmetry, I'm going to abbreviate, at x equals 3. Okay, now the next one, I can't tell the vertex by looking at it, so I'd have to use the formula. So h is going to equal negative b, which is 1, over 2 times a, which is 3. So that's going to be a negative 1/6. Now remember, that h value, that's the first part of the vertex. So the first part of the vertex is negative 1/6. Now if I had to plug that in, that wouldn't be very fun, but I don't have to here. If I'm looking for the axis of symmetry, I just need that x value. So who cares what the other part is, right? Here we're going to have an axis of symmetry at x equals negative 1/6. Okay? Now, we should also be able to find our intercepts. We're going to start with the y-intercept. This is a little bit easier. At every y-intercept, we said that the x value has to equal 0. So if we're trying to find a y-intercept without looking at a graph, all we have to do is plug a 0 in for x and figure out what's left for y. So here, if I put a 0 in for x, then I have 0 plus 7, which is 7. 7 squared is 49. Since y equals 49, that is where my graph will cross the y-axis. So we will have a y-intercept at 0, 49. 0 for x, 49 for y. That's a really tall one, right? If you were making the graph, you'd have to make a really huge graph to try to capture that intercept. All right, so here, the y-intercept plug a 0 in for x means we're going to have 0 squared, 7 times 0, and then minus 3. And what happens is these go away, and we're left with y equals negative 3. And actually, standard form, although it doesn't show us the vertex, is kind of nice because it does show us the y-intercept. So this last number here, right, if I plug a 0 in for x, these terms will always go away. So that last number, c, is always going to be where your graph of your standard form crosses the y-axis. C is always the y-intercept. So this one has a y-intercept at 0 for x, negative 3 for y. Okay? And then lastly, we have x-intercepts. At every x-intercept, y has to equal 0. So if I want to find x-intercepts without looking at a graph, right, and because sometimes they might be ridiculous numbers like 49, then I'm going to put a 0 in for y and solve for what's left. So if I put a 0 in for y here, x squared plus 4x plus 3, this equation that's left over, this is what we have been solving all along, right? This one is factorable. So if I factors of 3 that make 4 would be 3 and 1. This factors into x plus 3 and x plus 1, then I have a solution here of negative 3, and I have a solution here of negative 1. Those are the two places where my graph is going to cross the x-axis. So this is one of the reasons we call x-intercept zeros, is because those are the x values that zero out those factors. And then your x-intercepts for your function are the solutions to your equation. They are the same thing, okay? So this thing is going to have x-intercepts, or roots, at negative 3, 0, and negative 1, 0. Two nice places where this graph crosses the x-axis. Now if we look at this guy, if I put a 0 in for y here and solve, I'm not going to use the same method for solving, right? I don't want to have to multiply that out and then try to refactor it, but I can just take the square root. If I take the square root of both sides, then I have x plus 1 left here. On the other side, normally I'd put in a plus or minus, but there's no difference between positive and negative 0, so it's just a 0. So we subtract the 1 over, and then we get one solution, one place where this graph is going to cross the x-axis. So this has one root at negative 1, 0. Now why does that happen? Just think about this graph for a second, right? This is technically vertex form. Couldn't you tell by looking at it where the vertex was? I mean, I can. The vertex would be at the opposite of this number, which is negative 1, and then this number that's not out here would be 0. So if I had a vertex at negative 1, 0, negative 1, 0 is right here, and I knew this parabola opened up from that point, I could see that's the only point where this graph is going to touch the x-axis. Okay? So one x-intercept, one place where this graph crosses the x-axis. All right. Well, I didn't number these, but the third one here. The third one, let's see if I put a 0 in for y. I can use my square root method to solve this one again, but in this case I have to move the 5 over first. So I'm going to subtract that over, and then I have negative 5 equal to x squared. Now I can square root both sides, and now I have x equal to plus or minus. The negative's going to come out as an I, but I'm still stuck with a 5 there. So where would the roots then be for that function? How do I find I radical 5 and negative I radical 5 on a graph? Well, we can't. So what does that mean? That means if we have no real solutions, that means we have no roots, no x-intercepts. This graph's not going to cross the x-axis. So we still get solutions, but those imaginary solutions means your quadratic function won't touch the x-axis. So again, think about this. This is our vertex form. The vertex would be at 0 because there's nothing being added or subtracted in here in a parentheses, and then we have a 5 here. So I can tell this graph is going to start at 0, 5, 1, 2, 3, 4, 5, and I know because it's positive, it's going to open up from there. There is no way that parabola would ever touch the x-axis. So we can still solve and get solutions, but because they're imaginary, we see a graph that doesn't touch the x-axis. Okay, so one last one here. This last one, we're going to put a 0 in for y again and solve. And again, we can use our square root method, but we're going to start by subtracting over the 2. I don't want that to be it. Guys, I want this to be a -2 here. Just kidding. It's a little typo on the note sheet, otherwise it's not doing what I intended for it to do. Let's add the 2 over. Add the 2, add the 2. And let me do that again because I wanted that to be in green. Add the 2. That cancels. So now I have 2 equal to x minus 5 squared, square root both sides. And now x minus 5 equals plus or minus radical 2. And then add 5 to both sides. And that tells me that, let me go here, x is going to equal positive 5 plus or minus radical 2. Now, these are really roots, right? This is roots. Add 5 plus radical 2 and 0, and 5 minus radical 2 and 0. But if you were really trying to graph this function using those roots, do you have any idea where 5 plus radical 2 is? Yeah, me neither. So 5 plus radical 2 is about 6.4. So this is at about 6.40, and 5 minus radical 2 is about 3.6. It's about 3.6 and 0. Okay? So notice the variety of the roots. Okay? We got, in the first one here, 2 rational roots. Here we had 1 rational root. This would be 2 irrational roots, and then over here we had the 2 imaginary roots. The same 4 options that we had when we solved, we can have here in terms of roots. 1 rational root, graph crosses the x-axis 1 time, really nice, point. 2 rational roots, graph crosses the x-axis at 2 nice points. 2 irrational roots means the graph still crosses the x-axis twice, they're just not at exact points. And then those 2 imaginary solutions means our graph isn't going to cross the x-axis at all. Okay? So all that stuff we were doing, it all connects. The solutions to your equations have meaning for the roots or x-intercepts of